Now I'm going to solve a question related with linear regression. And as we solve this question, in some parts of the question, we are going to be learning now a couple of new, some very small topics that is related with linear regression. Anyway, so the question goes something like this. We have a process, and in this process, we manufacture a material, and temperature of the process is manipulated. So this is the phrasing is due to process engineering. We have a manipulated variable, temperature of the process. We can bring it to any value that we like, or within certain limits, any value. And when after we do that, we can not do anything about the process, and the process itself is going to manufacture the material required. And the material obtained at the end of the process, or at the end of the reaction, is the quality variable. So it's going to be the amount of or mass of the material at the end of the reaction, at the end of the process is the quality variable, whereas temperature of the process is the manipulated variable or process variable. And to determine a relation between them, empirical relation, a statistical model between them, we conduct a test, or we take a sample of 5 observations. So each 5 of these 5 observations will include a temperature reading, which is the manipulated variable, and a weight or mass reading, which is going to be the quality variable. So this is the description of the process from a process engineering point of view. From a statistical point of view, we have to convert this to the statistical nomenclature or statistical terms. So here, temperature, since it is independently change of the quality variable here, temperature is going to be the independent variable, or it's going to be the covariate, or it's going to be the predictor, or what did we call it, regressor. On the other hand, mass is going to be the response variable or dependent variable. Therefore, this is going to be what we call y, and this is going to be what we call x. And here we would like to determine the only model, or the mathematical model on the table is the simple linear regression model. Well, in reality, we have many different models when it comes to the wide palette of machine learning tools, but we are only considering here the simple linear regression case. So in terms of simple linear regression case, we are trying to, or we suggest a model of this type, where actually this error is going to be random error with 0 mean value and sigma square variance. So what we do not know in this model is this beta 0 and beta 1 parameter values and variance of the random error term. So using these sample of observations, or the data, the experiments of 5 observations, we would like to come up with the estimates of these values. So this is what part 1 asks. And in the second part, actually, as I said previously, we are always going to be able to obtain the least square line, but whether that regression is significant, whether there is actually a relation between x and y, is another story. And here note that this is going to be a causal relation, because this is the manipulated variable. We change x value, right? We have the power to change the x value, but depending on that change, y value is obtained automatically. And again, note that x value is determined by the experimenter. So it's going to be a mathematical constant. It's going to be this, it is going to be free of error. On the other hand, this is a response variable, a statistical quantity, because there's going to be random error buried on that output or response variable. And let me again remind you, the cause of this E might be, well, first of all, it may be due to the readings of this mass. If we are going to be using some laboratory equipment, some sophisticated experiments, right, not very straightforward experiments, is going to be human and or other factors which is going to cause fluctuations around the mean value. So there's going to be measurement error case, and there are also other nuisance factors during the experiment. There may be various changes in, for instance, flow rates. If there are some streams coming in and going into the process, and there might be some changes in process values around the optimal or the desired values, or surroundings temperature may be another factor, or many different factors which are called uncontrollable nuisance factors, which are going to affect the process. So they are going to also, these disturbances are going to enter through the statistical into the statistical model through random error term. All right. And the last part of the question is going to be determine 95% confidence interval on beta 0 and beta 1 values. Then there's going to be more to do with question, but I'm going to be explaining one more topic. So what I'm going to do is I'm going to try to solve it, but I'm going to use this Microsoft whiteboard. It is easier to use. So we had those 5 observations. I'm not going to write them again. What we need to do is, actually, we are going to be using this beta 1 hat is going to be equal to, I'm going to copy from the equation here. This is what we have obtained previously. For a simple linear regression model, this is going to be always valid. And beta 0 hat is going to be equal to, where is that equation? It's going to be equal to y bar minus beta 1 hat x bar. These are already found using least square analysis on a simple linear regression model. Therefore, they are going to be still valid. So what we need to find are to determine these two terms here. And syx is going to be equal to yx minus xi. I'm sorry, x bar, xr, yi from yi to n. And sxx is going to be equal to I from 1 to n xi minus x bar squared. And y bar is equal to 1 over ni from 1 to n. Let me leave some space here. It's going to be easier to write all the values here in between. Yi and x bar is going to be 1 over ni from 1 to n xi. It's that much straightforward. So yi values will be simply equal to all the values that is written here, plus, I'm not going to write all of them, 151 divided by number of observations, and here number of observations is equal to 5, sample size is 5. So this result is going to be equal to 0.400, I'm sorry, it's going to be 137 grams. Please note that I'm going to be also writing the units because it's an engineering problem, so I have to solve it in an engineering way. So when it comes to the sample average of x values, it's going to be 175.8 Celsius. The average temperature in which the experiments are conducted, and the average response value, right? A response variable value or dependent variable value, average mass value that we have obtained. So here, this is going to be basically equal to, can I take this? Move it to some other place. It's going to be easier, I guess. So let me take it here. All right. So let me move it here. This is going to be easier. Now, this is going to be, oh, we had y here. So that moving is that not very well built yet. Anyway, so this is going to be equal to, for each experiment, we have for the first experiment 130 yi value times xi minus x bar. Xi is equal to 165 minus x bar value is found here, 175 minus 8. Plus, we continue with the second experiment. It's going to be 133 yi value and the corresponding xi minus xi, and it goes like this until the last term, which is going to be equal to 155 times 212 minus 175.8, and the result is going to be equal to 830. And I again do not forget about the units, since these are temperature readings, x values, and the other one is mass. So mass times temperature is going to be Celsius grams, and sxx is going to be equal to, now I can write it here, this is going to be equal to 165 minus 178.8. Well, actually, if you like, you can, of course, use this relation here. 1 to n is going to be square minus n times x bar. So in this case, we can write it 165 square plus 167 square plus plus 212 square minus 5 times 175.8. Oh, we have a square here. I forgot. All right. So when we do this calculation, the result is going to be equal to 1955 Celsius square. Well, hopefully now we have SXX. We put it here and we take this value and we place it here. Therefore, this value is going to, let me get rid of that. And this value is going to be equal to, let's see, 830 Celsius gram over 1955 Celsius square. And again, be careful with the units. The result is going to be 0.425 grams per Celsius. Now, this is going to be the slope of the curve. This is going to be the what is called the partial effect. This is going to be the partial effect of temperature, inlet temperature on response variable, which is mass, on mass. What does partial effect mean here? If I make a change of 1 Celsius, 1 degree change in temperature, right? The corresponding change in mass is going to be equal to 0.425 grams. That's also the unit reveals also that result. You multiply it by 1 Celsius, it means a delta x change of delta x, or a change in x values. Delta x is equal to 1 Celsius, then the corresponding delta m value is going to be 0.425. So this actually gives an idea about the sensitivity of our process to the manipulated variable. And beta 0 value is going to be equal to y bar is 137 minus this beta 1, 0.425 times x bar, 75.8, and the result is going to be equal to 62.3 grams. Note that this should intercept, it should have the unit of grams, because the meaning of intercept is, so it's going to be a line like that. Intercept here, in this intercept, x value is actually equal to 0. So it means when temperature is equal to 0, this is going to be the expected value, or the estimated value of the slope. All right. So at this point, it is usually a good idea to draw the graph, but this is going to take a little bit of a long time if I do that here. So let me try. Nevertheless, I'm going to try to do that. 155, 165, 167. These are the corresponding x values, 180 and 212. So these are the temperature values, or you can also take them as x. And the y values are, which are actually mass values in grams, the corresponding mass values, the actual values are at 128. Here we have 1 point here. We have at 130 here, and this 130 will be here. Okay, another point. Of course, it's going to be an approximation. And at 170, we have 133. Okay, so at 180 is going to be 143. And the last of these is 100. Okay, let it be somewhere here. Let's draw it as much close to the correct scale as I can do. So this is going to be our last. These are the experimental points. And if I have done everything correctly, then the line that I should have come up with should probably look something like this. And not very bad. Of course, I cannot draw it very appropriately. So, well, as you can see, it is very difficult to see the intercept here because this should go to 0. And one thing which is pretty much out of the scope of this course, but you could have said that when temperature is equal to 0, are we going to have any production at all? Actually, we don't know that. Note that temperature is equal to 0 is very much out of this range. So this is something related with, again, with statistical learning, but we use those statistical models for usually for only the range that we have collected the data to train the model or to fit the model. So what I'm trying to say is that, as you can see, the range of the temperature values lies between 155 and 212. So in this case, we are only justified using this resulting model within that range, or very close to maybe these boundaries, including those neighboring values to those limiting values. But a value of 0 Celsius is very much distant from this region. And no one can guarantee that the same statistical model will also work here. So do not take this intercept as the response of the value when x is going to be equal to 0. Of course, as a statistical model, it says that mathematically, but do not take it seriously as a physical a prediction of what's going to become when temperature is taken as 0. So actually, we are only justified in using the statistical model, and therefore the estimated parameters here, again, within the values of x within the range of, let's say, 150 to 220 at most, within that range. So you cannot extrapolate, and actually in this case, 0 Celsius is extrapolating too much. You can use it only for interpolation. So only around this range we are justified in using our statistical model. So be careful about the reasoning about that. Okay, so once we find also another thing, if you have the equipment, or if you have the computer packages, for instance, to draw this, or you can draw it by your hand, you can see that actually. Let's see what about this beta 1 hat value. It is 0.425. Does that make sense? Actually, very approximately, you can see that there is a change of 151 to 128, kind of a change of how many, like 20 something, 23 units here in y direction, and in x direction we have very approximately how many units here. It's going to be like 57 units, right? So therefore, of course, this is just taking the extreme, only these values. But since, as you can see, these values seem to be, there seems to be little random noise here, because they seem to fit on this line, because I try to keep the scaling as good as it can be. If you divide this 28 by this 51 or 57, whatever this value, actually you can see that the ratio is somewhat pretty much close to 0.4 or 0.5. Therefore, we are on the right track. What do I mean by that? In some cases, for instance, students could, or anyone can easily make the mistake and write these the numerator and the denominator in the inverse way. So, for instance, if we had written these as 155, 1955, and 830, then this ratio would have come out to be greater than 2. Actually, if you have a scatter plot such as this one, you can easily see that since this is going to be the slope, right? Beta 1 hat is going to be the estimate of the slope. It doesn't, that value of greater than 2, actually greater than 1, does not make sense. And you can go back and check that this result is incorrect. So always have a visual understanding of the data if you can. That's the important point. Okay. So are we through with estimating the parameters? Actually, no, we haven't estimated this parameter yet. So in order to estimate this parameter, we have to find the residual values. Residual values are the distances between the estimated curve here, or estimated line here, and the actual values. So for instance, residual 1 is going to be equal to the real value of y1 minus y1 hat. And what is y1 hat? It is actually expected value of y given x1 hat. And this is basically equal to y1 minus beta 0 minus beta 1 hat x bar. So we are going to do the same thing for all the values. So let's write it generally for I value. So it's going to be I, where I is going to be 1, 2 to n. So using this notation, R1 is going to be equal to, very simply, Y1 is 130 is the actual value here, and the estimated value of Y1 is going to be equal to, so maybe let's first write the estimated value of Y1. It's going to be easier. It's going to be beta 0 hat plus beta 1 hat x1. So it's going to be equal to 62.3 plus 0.125. Please check with the table again. I'm not going to go back to the table. It's going to take unnecessarily long time. So the estimated value is 132.4 grams. What this means is this. Actually, when we are at 165 here at this point, the estimated value is at this point here 132. So this is the estimation of the expected value, or that the regression line between x and y. Note that here residual one is going to be equal to y1 minus, it's also equal to y1 hat. This is going to be equal to 128 minus 132.2. Note that we are going to have here, this is going to be the residual, the distance between the actual point and its estimated value on the regression line. This is going to be a negative value here, which is 2.4. Oh, I'm sorry, it's not going to be 138. It's going to be 128, 130. So it's going to be minus 2.4, because actually this point, this point should have been here. Actually, I'm confused about that. We are talking about the residual here. So it's not going to be here. The residual is going to be between this point and its projection on the estimated regression line. So using the same logic here, obtaining the y2 hat value, y2 minus y2 hat, is going to be equal to, I'm not going to go over all of them, it's going to be boring, minus this estimated value. If you use this regression formulation here, y2 hat is going to be found to be equal to 133.3, and we are going to have another negative but much smaller residual. Note that if your experimental values are close to the determined or estimated regression line, then the difference is going to be, of course, smaller. The residual is going to be smaller. And you find R3 value, which is going to be 4.2 grams, and R4. And note that the unit of residuals are going to be grams, because the units are going to be identical to the units of the response variable, and R5 is equal to 1.5 grams. One hint here, I'm not going to give you the proof of that, but these residual values should sum up to 0. Just an additional thing. Very simple stuff, actually, but I'm not going to go into that much proof here. It's not a magical trick. It's just due to, if you use the equations of the regression, this is what you are going to obtain. So let's see, what we are going to do is we would like an estimate of the noise, of variance of the noise term. So this is going to be equal to sum of square of regression divided by n minus 2. And sum of square of regression is basically, it is Ri, I1 to n square over n minus 1. Therefore, it is going to be equal to minus 2.4 square. Note that all of the minus negative terms are going to be turned into positive. That is the idea here. We don't want these negative values and positive values to cancel with each other. And this is going to be divided by n minus 2 here. And we have 5 observations, minus 2 is 3. So this is going to be equal to 8.53 grams square. This is going to be our estimate of noise variance. Again, it's a good idea to turn it into standard deviation. It's going to be equal to 2.92 grams. This is also called root mean square error. Root mean square error. And it gives a good idea about the noise of the system, noise level of the system. How much fluctuation around the expected value is to be expected. Okay, so the second part of the question, so this is the first part of the question. We are through with, we have found, let me show them again. This is one parameter of our model. And this is, let's see where the other two are. This is another parameter of our model, and this one is the another. So three parameters of the model, we have their point estimates. Of course, we have to check the significance of regression. Check significance of regression. Because the question again is, we have found these values, but is it just did we model noise, or is there really a significant relation between X and Y values? So basically the significance of regression hypothesis test is something constant. You do not take any other beta 1 value. So this is the frame of significance of regression test. So in order to do that, we just find it a T0 value, and T0 value here is going to be equal to beta 1 hat over estimated standard error of beta 1. This is going to be our procedure here. So beta 1 is estimated to be equal to 0.425 divided by the standard error of this term is going to be equal to, we have to actually go back and see. So let me show you the original equation so that all right, that's our question. And if we go back, we are basically going to be using this equation here. It's going to be sigma hat divided by standard deviation of sum of squares of in square root sum of squares of x. It's a little difficult, at least for me, to pronounce these. All right, if we go back, so therefore we are going to have this value here, 2.92 divided by square root of sum of square of x values. And where is that? I have found it somewhere. Note that you don't need to calculate again. Oh, here it is, 1955. This is the value that we need. And when we write it here, the result is going to be equal to, now this is going to be computed as 0.0660. And we have 6.44. Probably based on our experience, this T0 value is pretty much small. Nevertheless, let's check with the critical value. We are searching the critical value is going to be, we are basically conducting this test again at the significance level of 0.05. So it's going to be at the 0.025 two-sided hypothesis test confidence level with 3 degrees of freedom. Pay attention to that. We have 3 degrees of freedom because this is n minus 2. N is equal to 5. Therefore, this value is going to be equal to 3.13. And since this value is greater than 3.13, we have this following conclusion. We say that regression between temperature and maybe it's better to write it in the opposite order, mass and, oh no, temperature and mass is better. Temperature and mass is significant at alpha is equal to 0.05. Okay, well, to give an idea about the p-value, we can find the p-value. So 0.025 with 3 degrees of freedom. I'm sorry, 0.00. I have to keep track of these number of zeros carefully. Is equal to 7.45 greater than T0, which is equal to 6.44, which is greater than T0.005 with 3 degrees of freedom, which is 5.84. Okay, this seems to be okay. So therefore, since this is going to be p-value over 2 is smaller than 0 0.005, but not smaller than 0.0025, which leads us to the conclusion that 0.005 smaller, p-value smaller 0.01. Okay, so our p-value for the regression here, and note that we also can of course find the p-value since this is an hypothesis test. So the p-value of this hypothesis test lies between those two values, which is pretty much a low value, so that we can, I think, very easily deem significance to this test. Now, finally, we are going to determine the confidence intervals for beta 0 and beta 1. And they are already given as the equation, so I'm just going to copy them here. So what we are going to obtain here is we have for instance, for beta 1, we have its point estimate, which is 0.425, and we are going to be subtracting this value from the t value that we have found, as you can see here, 3.18, multiplied by the standard deviation or the standard error term here. So it's going to be 2.92 divided by 1955. So this is going to be smaller equal beta 1 smaller equal 425 this time plus, and if we compute this quantity as a whole, this is going to be equal to 0.210. So the probability that beta 1 lies within that interval is going to be equal to 0.95. Of course, you can always change the significance level, therefore you're going to be changing the t value. The same calculation will be valid. So therefore, the resulting confidence interval for beta 1 is going to be equal to these values. Of course, it's a good idea to also write the unit, which is grams per centimeter, I guess. And note that we can also use this result as an alternative to hypothesis test. The hypothesis test for significance suggested that beta 1 is equal to 0 for the null hypothesis. And since beta 1 is equal to 0, does not lie within the interval, we reject the null hypothesis, which says actually the regression is non-significant, and we say that regression is significant. So when it comes to finding a confidence interval for beta 0, it's going to be again the point estimate of beta 0 and the t alpha over 2 value. And now this time, this whole relation is going to be the standard error of standard error estimate of the beta 1 head value. So by the way, I'm trying to copy from my notes here these numerical values. So how did we get these results? Actually, this is 1 over n. It is, again, let me show you where we have obtained this. All right. It is actually this value here, exactly. So we use the standard deviation estimate here, and 1 over n, we have x bar square and sum of square of x values. And note that we have already calculated these quantities in order to determine beta 0. So the nice thing about this is the quantities that you have used to determine beta 1 and beta 1 0, which are x bar here, sum of square of x values. And of course, we should calculate the standard deviation estimate. Once we calculate all of those, you don't need to calculate them again to obtain the standard error of beta 0 head and beta 1 head terms. So let's go back to our calculations. All right, this is going to be smaller equal beta 0 smaller equal 32, and this value is going to be equal to 37.2 plus 37.2 is equal to 0.95, and the result here is going to be 25.2 smaller equal beta 0 99.5 and the grams with 95% confidence level. Note that we do not say anything like beta 0 is equal to 0, does not lie in this interval, so the regression is significant. Actually, we don't care what, that's got nothing to do with the significance being, the regression being significant or not. because where is the intercept, whether it moves through beta 0 or whether it goes through the origin or any value above or below the origin, that has got nothing to do with significance. There are some actually interesting tests related with our hypothesis test of such may have a meaning, but I'm not going to go into that. There is a special meaning for that, but I'm not going to go into that. But that has got nothing to do with significance of regression. Therefore, we don't add anything like beta 0 is equal to 0, does not lie here, so regression is significant or anything like that. I'm going to stop with the question, and I'm going to talk about another statistical formulation, a very short one. Then I'm going to continue with the question. The thing that I would like to talk about is what the so-called prediction interval on future observation. Now, this is something, the concept of prediction interval and prediction is something we haven't covered up to this point. There was only a bonus video I prepared. I'm going to give you the link in chapter 7. I remember in lecture 7, chapter 8, related to chapter 8, I guess. So in that, I highly recommend you to watch that video, although it's not included within the regular curriculum of this course. So you're not going to be responsible for that in the exam. It's going to be pretty much important to understand this topic. Therefore, we are going to come up with again an interval, as you can see, a left-hand side and a right-hand side confidence bounds, but this time the confidence bounds will be for a future observation y0. What do I mean that? First of all, let's see this, what this may be confused with some other thing that we have covered. Now, this may be easily confused, but confidence intervals on mean response. Here we had on the left-hand side another limit, on the right-hand side we had another bound here. And here we had expected value of y given x0. This time, instead of that, we have y at x0. This is the very important distinction, but that's a crucial distinction. Now, note that this is a population parameter. Expected value of y given x0. When I write it like that, I think it is more obvious that this is a population parameter. It is just like mu for a single variable process. Now here, given x0 value, the controlled variable that we manipulate to a certain value, therefore what, and since y is the random variable here, we are trying to determine its expected value, and therefore we try to come up with a confidence interval. So this is very much like confidence interval for mu for single variable processes that we have covered in I guess 3 to 4 lectures and chapters. Here, on the other hand, the question is different. This is an individual observation. And y0 here means the y value at x0. Now, as opposed to the other case where we obtain the confidence interval for the mean response, in the other case, actually, let me remind you what the other case actually determines. If this is the real expected value, let's put it, this is the estimated one, using estimated regression line, using some sample data. At any point x0, the confidence interval that we found related with expected value of y given x, here we refer to the location of this line here. So where can this line be? With a 95% confidence interval, we are going to say that this line will pass through, when you give a value of x0, this line may pass through any point here with 95% confidence interval. That's what is meant by this confidence interval on the mean response. On the other hand, what is meant by the prediction interval is we are now referring to single observations. When x0 is given, or we are going to test a future observation. Here we haven't tested yet, for instance. We are going to conduct a test at when x is equal to 0. We might have conducted tests at those levels of x0. That's not important, but we are going to be conducting a new test. If this is the case, note that a new test may be anywhere here in a wider region, because it's not going to be only the expected, the mean value that we are interested in. We are interested in the single observation value. Therefore, there's going to be the noise effect directly affecting here. The variation here should be the smallest variation can be only as small as variance of noise. So the total variance due to the uncertainties of the estimation procedures, uncertainties carried by the estimation procedures or brought by the estimation procedures, the resulting uncertainty is going to be even larger than this value. That's why here we have 1 here. Actually, even if these terms were equal to 0, then we would be multiplying this t value by standard deviation estimate of the noise. Therefore, y is going to be between those two values. But even this uncertainty is greater than the uncertainty of the or the uncertainty brought by the noise. We have also, due to the uncertainty due to beta 0 and beta 1. So all of these parameter uncertainties also carry. So this is going to be the prediction interval for a future observation. So let me try to explain this on example. Find the 95% confidence interval for the mean response and 95% prediction interval for a future observation at x is equal to 180. So what the question asks is basically, actually, let's remember that that was basically somewhat like our estimated regression line. When x is equal to 180, what could be the confidence interval for this line itself? This is the first part of the question when it says confidence interval for the mean response, which refers to this line. So it is the expected value of y when x is equal to 180. What is the confidence interval for that? And what is the prediction interval for a future observation at x is equal to 180? What is the prediction interval when x is equal to 180 for y? And there's a very interesting point here. Note that in prediction interval, the quantity for which we would like to determine the interval itself is a random variable. Whereas actually in the previous cases for confidence intervals that we have determined, the confidence intervals we have determined, these were not the random variables, but the upper and lower confidence bounds were the random variables. So it is just to distinguish between those two concepts, which are, I think, pretty much easy to confuse. So I'm going to again shift to Microsoft Whiteboard, and that actually pretty much sounds like a commercial, but it's not actually. So what we do is, first of all, the question actually asks confidence interval of mean response and prediction interval at x0 is equal to 180. We should have a unit, I think, Celsius. All right. So the equation that we have found, y hat, which is equal to expected value of y given x hat, is equal to beta 0 hat plus beta 1 hat x. And we have already determined this. I'm going to copy the values here if I can find them. And they are going to be equal to 62.2 grams. I'm also going to write the units to make it easy to see what's going on. Grams per Celsius times x. Again, x is going to be in Celsius. So this is the regression equation, which is going to be y hat, which is going to be in grams. This is the regression equation. Note that it's an estimate that we have come up with using the sample. Note that it is just like sample mean. So an estimation using the sample. These are not the true values. We do not know the true values. So that's why we would like to determine a confidence interval for this value when x is equal to 180. So what we ask is, what is this equal to? A confidence interval, 95% confidence interval, of course, I'm asking 95% confidence interval for this quantity is equal to what? So what we do is we simply use the corresponding equation, which is actually, if we go back here, all right, let's see. Okay, here it says We need, of course, the corresponding t value. We need the standard deviation estimation, variance estimation. It's going to be 1 over n and x0 minus x bar. Note that this quantity itself will depend on this x0 value, which means this, as x0 changes, the confidence bound or interval here will also change. So that's an interesting thing. So this is not a constant value, which means actually we don't have a confidence bound such as these constant bounds for any x0 value. The same width is going to be found. That's not the case. Depending on the x0 value, we are going to have a different x0 confidence bound. And more than that, we can analyze this. Note that this is the contribution of x0 here. So as this deviation from x bar value is larger, we are going to have a wider here, actually a larger value here and here. Therefore, we are going to have a wider confidence interval. So basically, that's the typical case for linear regression. If this is your estimated linear regression line, then the corresponding confidence interval on the mean response will be like this. So if this, maybe I should have used the other whiteboard to use different colors. But what do I mean by that? As x0 is close to x bar, and x bar should be somewhere here, right? Because if you are taking measurements probably at different locations, x bar is going to be quite possibly in the middle or in the center region, somewhere here. So around the mean value, you are going to have the smallest confidence bound. You are going to be more sure of the results there. These are going to be more reliable results. Therefore, confidence interval is going to be smaller there. X0 is, if x bar is almost equal to x bar, x0 is, note that this term will cancel. You are going to have a smaller confidence interval here. On the other hand, as you go here and here to the right hand side, to the left hand side, then your confidence bound seems to get, not seems to, but get broader. That's why actually I have already talked that the linear regression or any statistical model is valid for interpolation purposes, not for extrapolation purposes. Actually, and extreme extrapolation is strictly forbidden. One of the reasons is, that's not the only reason, but one of the reasons, as you can see, is as you move away from the center of x values, right? If you move further, these confidence bounds, confidence intervals is going to get larger and larger. And they are going to be, actually, it means that here and here, so extrapolation regions, in extrapolation regions, we are going to be much less sure of our result. So the reliability is going to drop drastically. That's one of the reasons why the statistical models are good for interpolation, but not for extrapolation. All right, now let me continue with the question. Okay, so I'm going to be using that equation, and using this equation, actually, first of all, I have to find the y value at 100. X is equal to, well, actually, I don't need to write x because it is only a variable of x, so I can easily write it that way. So it's going to be 62.3 plus 125 times the x value corresponding, which is equal to 180. When you do the calculation, the result is found as 138.8 Celsius. So this is our point estimate for the response variable when x is equal to 180 degrees. Now, what I would like to determine is that, again, this is equal to expected value of y given x0 is equal to 108 Celsius estimate. And again, note that this is the estimate of the location of the regression line. How much could this value could have deviated? This is the question. So our confidence interval is going to be this point estimate minus 3.18 is the t value. And now I'm writing here the associated standard error here, 8.53 1 over 5 plus 180 minus 175.8. So actually, you can see that this point 180 is near the center of the, or the whole, the bulk of the x values, the mean values. Therefore, this is going to be some of the most precise estimation that you can obtain. 1.995 was the point. I think that wasn't the point. That was 1955. Let me see. Yes, we don't have a decimal point here. 1955. And this is smaller equal expected value of y given x0 is equal to 180, right? Smaller equal 138.8. The very same thing written here. So I'm going to find this value is 4.24, 4.24, and the probability of this confidence bound to have that quantity here is 0.95. Therefore, the result is going to be equal to 134.5 xy x0 is equal to, or x is simply equal to 180 Celsius, and the upper bound is going to be 130.0 grams. So this is going to be our confidence interval for the mean response, which means, I repeat again, if this is our figure, and if this is where 130 Celsius is, all right, then the corresponding point estimate here is equal to 138.8 grams. On the other hand, it is possible that this mean response could have been 134.5 and 143.0. What do I mean by the response? The expected value, not a single observation. A single observation will be buried with individual random noise elements. We get rid of when we take the expected value. So this is the estimate of the expected value, where this line will be. On the other hand, this does not say that when we conduct an experiment at 180 Celsius, that single experiment result with 95% probability. Of course, this is again at 95% confidence level. I do not mean that with 95% confidence level, that single observation will fall in that interval. That thing that I'm asking is actually determined by the prediction interval. So prediction interval, I'm not going to go to the equation again, just check that it's going to be correct. For the prediction interval, the equation turns into, again, the point estimate, the very same thing, again, the same statistics value in square root. This time, we are going to have standard error is going to, parenthesis should have been closed, it's going to be equal to 8.58. Actually, it's going to be very similar. The very same 1 over n here is here, plus this very same value is still here, right, divided by 1955. But there's going to be addition of 1 here, and that 1 here will correspond to the uncertainty brought by the noise term, the individual noise term, and this is going to be smaller equal to, let me get rid of this right now so that I can use this. So this is going to be equal to y value at what was the value at x is equal to 180 Celsius. It's going to be smaller, 138.8 plus, okay, what's this value? I should have computed in my calculations, minus, I'm sorry, 10.2. So this is plus 10.2. Again, in probability is equal to 95. And when we do the calculation, we obtain this value. So let me not write it. It's probability. Let me write it in the result form. 0.y0 grams. Well, compare it with this value here, this one with this one. As you can see, the mean response, confidence interval for the mean response is much narrower compared to confidence interval for the individual observation. So I repeat again, so this is going to be, let's say, for the specific value, I'm not going to write again, this is going to be our confidence bound for the expected value here. It's going to be this line here. On the other hand, the confidence the prediction interval is going to be between those two. This is too much similar color. Between those 2 points is going to be a much broader range, right? Because now we are talking about individual observations. Therefore, with 95% probability, we expect that the individual observations will fall in this range. On the other hand, with 95% probability, we expect that this actual line will be between those two values. Now I'm going to talk about the last topic related with this issue, which is going to be R-square statistics. Up to this point, I have not talked about any statistics or any method to assess the quality of the fit, or in statistical terms, quality of the fit or goodness of fit. What do I mean by goodness of fit or quality of fit? Think about two cases where we have this experimental data. This is the first case, let's say. And in the second case, our experimental data is like that. And note that these are, let's say, from two different unrelated experiments: temperature versus concentration, velocity versus, I don't know, some force thing. And in two different fields. And in this experiment, we obtain a regression line such as this one, let's say. And for this example, for this experiment at the end, we obtain this regression line. Now the question is, which one of these regression lines seem to be of higher quality? Which of these fits seem to be higher quality? Just by visual inspection, we can easily say that this seems to have a higher quality of fit, which is, in statistical terms, this should have a higher goodness of fit. So how can we assess this using mathematics? R square is actually a value used for that. R square is basically equal to sum of square of regression terms, and I haven't talked about this previously, divided by sum of square of total terms. Now, sum of square total is very easy to define. Let me first talk about it. It's basically equal to this thing. So basically, it is equal to sum of square of y terms, right? So it's the variation of y, but we don't divide by the degrees of freedom of y. So it's just y values subtracted from y, sample mean and squared and added together. So this is sum of square total variance variability of the response variable. And this is what we would like to explain in linear regression. Sum of square regression is actually, note that it's not, although the subscript is r, is not residual, it is actually computed as b1 square I from 1 to n xi minus x bar square. But we are not going to use this equation because this is going a little bit more into linear regression analysis more deeply, I may say. Not very much, but we have already an alternative method to compute that, already something that we are familiar with, so I'm not going to use this one. Instead of this one, you can write this equation as 1 minus sum of square of residuals over sum of square of t. So therefore, r square is basically 1 minus sum of square of residuals is I from 1 to n yi minus yi squared. Each of them is, note that the residual, divided by yi minus y bar here. There is no I here, of course. Now, what is the meaning of this equation? Now, this is the total variance that is waiting to be explained. And this is the variance not explained here. Why do I call it not explained? Because these are the residual terms. Our explained part are these estimations. And the residuals are the unexplained part. But when you square them and add that together, you have this part is the total unexplained part. Total unexplained variance. And this is the total variance. So the ratio of them would be the ratio of unexplained variance. When you subtract from 1, this is going to be the ratio of explained variance of y. Therefore, r square is going to be, well, what it means statistically is this one, but in other terms, since this is a metric to measure how much variance is explained, this exactly serves our purpose. Therefore, it will give an idea about the quality of the fit. And what do I mean by variance explained, unexplained? Think about it that way. So if your points are close to this regression line, to this estimated line, therefore the variance here, note that the variance here corresponds to, forget about the x values, it is this variance here of y. And how much of this is explained? Only these very small variances are not explained, right? Those additional residual parts, which are the distances between the projections on these lines and the actual observation, they are very small. Compared to that whole variance, they are small. Therefore, 1 minus this ratio is going to be the explained part. R square is going to be high. But on the other hand, if these values were here, then now the variance is going to be between those two. This is actually range, not the variance. Here we are talking about the y-axis projection here, but I think you got the idea. You can find the variance here. But now compared with the residual values here, actually, as you can see, the residual values, they are going to be computed as this point and its projection on this, actually on this line. But if you just put a vertical line, wherever this point is equal to, in terms of the y value, this difference is going to be the residual. Anyway, the residual squared values, summing them is going to be make an important contribution to the total variance value. Therefore, there is a significant amount of unexplained variance here. Therefore, R square value is going to be small. And basically, using this logic, R square will be between 0 and 1, including these values. 1 is only achievable, well, if you have a perfect fit. Let me put it that way. If your exactly experimental points exactly line on the regressor, on the regression line, then you have R square is equal to 1. And no fit means that beta 1 is assumed to be exactly equal to 0. I said that due to if you take infinite number of significant figures, that is impossible. But for if you have take a small number of significant figures, that is still possible. Anyway, beta 1 is equal to 0 is going to have 0 R square, and the other case is perfect. But in real life, usually we obtain values between those two. We can say that actually R square, although R square is 1 is a very rare thing in real life that we can obtain. Usually R square values between or about 0.9, 0.8, these are very good fits or excellent fits, I may say. Good fits, let me say. Whereas R square values between 0.5, 0.6, I may say, maybe also including 0.4, are moderate fits, moderate quality fits. And R square values 0.3, smaller than 0.3 are, we may say, poor fits or poor quality of fits. And there is another issue I would like to point out here. Let's not confuse R square with the significance of regression. Now, significance of regression is actually like all hypothesis tests. They are dependent on the value of n, right? For small n values, it is, for instance, difficult to obtain a significant regression value compared to larger n values, like all the hypothesis tests. And this is related, if you go back to the concept of hypothesis test, this is all related with the t distribution and the degrees of freedom in t distribution, and also related with the standard error term, because we have 1 over n in our standard error term, and we would like this to be as small as possible. Therefore, n should be large number. Anyway, but as you can see, this has got nothing to do with n. Actually, both here and here we sum over all possible values. So it's going to be this ratio cannot be biased to a high or low value depending on the value of n. Well, there may be small biases, but that's not what I'm trying to say. Anyway, so R square, as I said, does not show the significance of a regression. What do I mean by that? A regression may be significant, yet a small R square value may have been obtained. For instance, it is possible that R square may have come out to be equal to 0.05, yet still this regression may be significant. In this case, it means that there is a relation between x and y, right? But that relation is very poor. That is what it means. On the other hand, it is also possible that you may have a high R square value, but non-significant regression.
In this case, you do not say that R square value is important. You say that the significant of regression isn't found to be significant. Therefore, R square value will not represent the relation between, or the strength or the quality of the fit. Because as I said, we couldn't find, first of all, the significant, we couldn't show that the regression is significant. So the first step should be showing that the regression is significant. After that, you can have a look at the R square value and have an idea about the quality of the fit. Okay, so if we find R square for the previous question, it's going to be very straightforward. Sum of square of error over sum of square total. This is what we would like to obtain. This is 1 minus sum of square of error. We already know this value. This is found to be equal to sum of square residues, I'm sorry, 25.6. This value is computed using this equation to be equal to, so this is the only thing that you need to compute for the R square value, right? And the result is going to be equal to 0.99, an unrealistically high R square value. So we are going to say that therefore an excellent fit. Note that this is the first time we are saying something about the quality of the fit here.